Hello, it's Stat 134, Lecture 6. So last time we started section 2.2 on the normal approximation to the binomial. And remember that for binomial, the mean mu is NP and standard deviation sigma is square root of NPQ, where Q is 1 minus P. And so under the normal approximation to the binomial, if we're trying to approximate the probability of success between A and B successes, that we're going to have a continuity correction here where we're actually going to integrate the normal curve from A minus a half to B plus a half. And the reason for that is because we want to approximate the shaded area here. And A and B are in the middle of the block, and each block has width 1. So we need to start 1/2 to the left of A and 1/2 to the right of B. And so in standard units, then we take B plus a half minus mu over sigma, find the CDF of that, and subtract A minus a half minus mu over sigma, CDF of that. So we did an example here where we're looking to find, to approximate the chance of getting 75 sixes in 600 rolls of a fair die. And so here I'm going to do a continuity correction where I'll take 75.5 minus 100 over 9.1, CDF of that, minus 74.5 minus 100 over 9.1, CDF of that. And you can see that the binomial is very close to that. So today we're going to go over student answers to the concept test from last time, finish section 2.2 and section 2.4 on the Poisson approximation. So last time we did this question: if your coin is tossed and you win $1 if there's exactly 50% heads, which is better, 10 tosses or 100 tosses? So the answer is that it's 10 tosses. So one person writes that it's 100 tosses because, according to the law of average, as the number of tosses increases, you're more likely to be closer to 50%. So that's absolutely correct. That is what the law of averages, or the law of large numbers, says, as I can show you in the statement below. But that doesn't actually tell you which is better for finding the probability of exactly 100. I mean exactly 50%. And the reason is because, so let's say that we're looking at the proportion of heads for both 10 and 100 tosses. And so the law of large numbers, or the law of averages, says that basically the peak around P is going to be steeper as n gets larger, so that the probability that you're within epsilon of P goes to 1 as n goes to infinity. But the thing you have to realize is that that interval between P minus epsilon and P plus epsilon, that is an interval of proportion of heads. If you want an interval of heads, you'd need to multiply that by n, which is a huge number. So you're going to get a large interval of the number of heads. So to get exactly P times n number of heads is actually quite small. So one person writes, far more spread out for n is 100, more possibilities for not exactly 50%. Imagine the question was n is 2 versus n is 100, and it's even simpler. And another person made a shout out to their ma that they got it right. So here's another concept test to make sure you're on track here. A fair coin is tossed, which is more likely, between 4 and 6 heads in 10 tosses, or between 40 and 60 heads in 100 tosses. And so here the answer is B. And one way to think about it is that I'll just write here that these intervals are approximately mu plus or minus 1 sigma and mu plus or minus 2 sigma. And mu plus or minus 1 sigma for the n is k case, n is 10 case, is 68% approximately, and for the n is 100 case, it's 95% approximately. That's by the empirical rule. So option B is more likely. Okay, so now on to normal approximation to the binomial distribution. How do we relate the normal distribution, which has two parameters, to the binomial distribution, which has two parameters? Well, mu is np and sigma is square root of npq. Furthermore, when can you do a normal approximation? So the answer is when n is 20 or greater than 20, so that it is really approximately normal. And also, you need mu plus or minus 3 sigma to be between 0 and n, so that your normal curve fits between 0 and n. So for example, if you want to see whether binomial 21 over 10 should be approximated, well, n is 20, that's good, but mu minus 3 sigma is less than 0, so that's not good, and your binomial distribution will look skewed to the left, as you can see here, and it's not good for a normal approximation. So here's an example. Southwest overbooks its flights. You calculate here that that the average is there's 360 tickets sold, and the likelihood that someone shows up is 0.9. So on average, 324 people show up with a standard deviation of 5.7. So if x is the number of people who show up, this is binomial 360.9, and you can indeed approximate it by normal, because 324 plus or minus 17.1 is between 0 and 360, and then so the probability that there's at least one empty seats, the probability that there's less than or equal to 349 people who show up, and we do a continuity correction here, and so we get phi is 4.47, which is very close to 1. So now we're moving on to Poisson. So Poisson is in the case when p is small, or p is close to 1, and n is large. So binomial np, we're going to approximate by Poisson mu is np. And so you can see in this picture the situations where you can do a Poisson approximation. So here, the Poisson with the parameter mu is defined as the exponential to the minus mu to the k over k factorial for infinitely many outcomes. It's discrete, but it has infinitely many outcomes. And so here's an example. So you bet 500 times independently on a bet with a 1 over 1,000 chance of winning. The probability that you win more than one bet, you can figure that out exactly, or with a Poisson, and you'll get very close answers. So the Poisson p of 0 is e to the minus 1/2. And so there you go. Now what happens if p is close to 1? Well, in that case, q is close to 0. So we're going to want, so binomial nq is going to be close to Poisson mu nq for n large and small q. So for example, in this problem, where 97.8% of approximately 30 million families have a fridge, you're going to want to say that, think of that, because 97.8% is, that's our p, that's close to 1. We want then to to say that 2.2% of poor families don't have a fridge. So in this case, so we want the probability that 98 or more have fridges, or equivalently that 2 or less don't have a fridge. So the chance that they don't have a fridge is, as we said, Q is 0.022, and this is P is 90.978. So, right, so all we need then is a probability that 2 or less don't have a fridge. And so we can compute each of these Poisson just using the formula. So here's a picture of Poisson 1 as a limit of binomials as n goes to 0 and as p goes to 0 and n goes to infinity and np goes to 1. So you can see it's getting closer and closer. You have 10 times 1 over 10, 100 times 1 over 100, 1,000 times 1 over 1,000, and you can see also the distributions approximate the bottom one. So finally, suppose that you and I have a box with 600 marbles. In my box, 4 of the marbles are black and 3 of your marbles are black. We draw 300 with replacement. What is the chance that I draw the same number of black marbles? So we're told to approximate this, so we're going to use Poisson. And we're looking for the probability that x is y. And because we're drawing with replacement, the values that that we may draw of black marbles is between 0 and 300. So we're just going to apply the addition rule and independence because we're drawing with replacement, and then just our Poisson formula. Okay, have a great day. I'll see you next time.